for real zeros of polynomials. So the rational zeros theorem says that if a polynomial has integer coefficients, then every rational zero of that polynomial is of the form p over q, where p is a factor of the constant, the last term, and q is a factor of the leading coefficient. So here we have the polynomial in its factored and expanded form. We see in its factored form very easily what our zeros are. If we set each of these equal to 0, we're going to get zeros of 2, 3, and -4. Or x-intercepts, interchangeable words. What we can do is compare that to that rational zeros theorem. So the rational zeros theorem is saying that our p's are going to be the factors of our constant, and our q's are going to be the factors of the leading coefficient, which is 1 in this case. So our factors for p, we have plus or minus 1 times plus or minus 24, right? Depending on whether it's positive or negative. They could both be negative or both be positive. 2 times 12, we could have 3 times 8, or we could have 4 times 6. And then for q, we don't have a lot of options to multiply to 1. It's either 1 times 1 or -1 times -1. So what we want to do is look at our possible rationals, which is our list of p's divided by q's. So I'm going to divide each of those p's by that plus or minus 1. And since that's a nice easy division, it's going to look like the same p list in this case. Plus or minus 1, plus or minus 2, plus or minus 3, 4, 6, 8, 12, and 24. And while this is a long list to go through, I do recognize that 2, 3, and 4 all happen to be on my list, and they are in fact zeros. If the polynomial has the ability to be factored the way we know in Algebra 1, that is still going to be the ideal situation. But this is going to give us an alternative when we can't factor it the ways we already know how. So what we're going to do using these rational zeros is list all the p's over q's out and use synthetic division to check if you get a remainder of 0. If you get a remainder of 0, then yes, that is going to be a 0 or an x-intercept of my function. So here we want to find all of the rational zeros of this function. We have x cubed minus 3x plus 2. So let's list our p's and q's. Remember, p's come from the end, q's come from the beginning. So my p's here are plus or minus 1 and plus or minus 2. My q's are just plus or minus 1. So my p's divided by q's are 1 over 1 and 2 over 1. So what we would do is use the synthetic division to check if these are in fact going to be zeros. So I can start with 1, and I'm going to use the coefficients here. Just don't forget we're missing that x squared term, so we put in a 0 as a placeholder. 1, 0, -3, 2. All right, so we're going to bring down the 1, multiply, add, multiply, add, multiply, and add, and sure enough, I get a remainder of 0. Okay, so that means that 1 is going to be a 0 of my function. So if I wanted to find the rational zeros, I could keep going through this list, or I could see if I can factor this any further. But I could keep going through this list if I wanted. So for example, I don't know, let's pick another random number. We could use -1 or 2 or -2. It doesn't matter. Maybe I try a -1 next. So at this point, I have some options. I could go back to the original equation, which is fine. There's nothing wrong with that. Or I could consider the fact that this has kind of started to simplify my equation, right? The synthetic division is really like saying x minus 1, which is the factor that gives us the 0 of 1, times that quotient, x squared plus x minus 2. So I could absolutely think of it this way. So this synthetic division I could do, but honestly, at this point, it's kind of silly because I can keep factoring the way I know how from Algebra 1. So why waste my time? So that's going to give me, let's see, we have the x minus 1, and then that's going to be x and x. They have to multiply to -2, but add to +1, so 2 and -1. So that's fully factored, or we could say x minus 1 squared and x plus 2. So that means that my zeros are going to be 1 and -2. And you can kind of see how this is going to tie into 4, 2, where we then graph this. All right, so let's try again. Let's factor. So we have our p's and our q's. So my p's are going to come from here. My q's are going to come from here. So we have for p's plus or minus 1 times plus or minus 6. And then we have plus or minus 2 times plus or minus 3. Our q's are plus or minus 1 and plus or minus 2. Those are the factors of 2. So our p's divided by q's, we have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. And then we also have plus or minus 1 over 2, plus or minus 2 over 2, which actually we've already gotten with that 1. Plus or minus 3 over 2, and plus or minus 6 over 2, but 6 over 2 is actually 3, which we already have accounted for. Okay. All right, so there's my list of possible rationals. So let's just start with synthetic division. It does not matter what number you start with. If you want to start with 1, you want to start with 2, you want to start with whatever, it's up to you. So let's say I start with 1. So I have 1, we're going to use those coefficients, so that's a 2, 1, negative 13, and 6 from here. Bring down that 2, 2, 3, 3, negative 10, negative 10, negative 4. This is not going to be a 0 because I do not get 0 as my remainder. All right. Now it does give me some useful information though. If I think back to one of my earlier theorems, this really means that when I plug 1 into the function, my answer is negative 4. So at the very least, when I go to graph this, I will be able to use that information to plot a point on my graph. So it wasn't useless. It just didn't get me where I wanted to go. I don't know, maybe I try 2 next. 2, 1, negative 13, and 6. So that's 2, 4, 5, 10, negative 3, negative 6, 0. Perfect. There's my remainder of 0. So that means 2 is going to be a 0 of my function, and I can think of this as now being somewhat factored. That really means x minus 2 is the factor. If 2 is the 0, right, we change the sign. This, remember, is my remainder. This is my quotient, so that can be 2. I go down a degree, so x squared plus 5x minus 3. If I can factor this by hand algebra-wise, I absolutely should. If I can't, I could keep going, but I can, right? I can definitely factor this. That's going to be 2x and x. And for the 3, it's going to be a 1 and a 3, so we'll go with positive 6 and negative 1, and that should take care of it. So we are fully factored. If we needed to from here, we would be able to graph it. All right, let's take a look at our next one. So again, we want to find the zeros, and then we're actually going to graph this one. So p's and q's. P's, q's. My p's are 1 times 10, plus or minus, and 2 times 5. And then our q's, luckily, are just 1, which is so nice to not have to do any fractions. All right, so when I do my p over q list, we've got 1 over 1, 2 over 1, 5 over 1, and 10 over 1. That really is 8 different numbers that I could be trying here. You can pick anything that you would like to start with. To save time, I already know something that's going to work just because I've worked these out already. But you might be here and test them all until you find something. So I know negative 2 works, so I'm going to start with that. So negative 2, we've got, let's see, that's a 1, a 5, or sorry, a negative 5, another negative 5, a 23, and a 10. Okay, so we get 1, negative 2, negative 7, 14, 9, negative 18, 5, negative 10, and sure enough, there's my 0. So it's getting me started at least. That x minus 2 is a 0 for my graph. So if I'm going to kind of sketch this simultaneously, I can plot that negative 2 on there. Okay. I also can take a look and kind of continue to factor this. X minus or x plus 2 is going to be the factor. And then I go down a degree. So it was the 4th. Now we're to the 3rd. 1x to the 3rd minus 7x to the 2nd plus 9x plus 5. I still don't know how to factor this though. So it's up to you. I can actually, I I can kind of just pretend now this is the problem that I have to factor. So I can rework my P's and Q's list, right? Because I'm factoring something smaller. So these are going to be my P's, and these are going to be my Q's. So I have P's is plus or minus 1 times plus or minus 5. My Q is just plus or minus 1. So my list has greatly shortened. I'm just doing plus or minus 1, plus or minus 5 as my options. Okay. So now this is what I want to synthetically divide to see if I can factor that part anymore. So maybe I pick, I don't know, maybe I pick 1. So we have 1, negative 7, 9, and 5. 1, 1, negative 6, negative 6, 3, 3, and that is going to give me, let's see, 8, so that's no good. Okay, that doesn't work. Maybe I try 5. So 1, negative 7, 9, and 5. 1, 5, negative 2, negative 10, negative 1, negative 5, 0. Perfect. So 5 is going to be another 0 here. 1, 2, 3, 4, 5. Okay, so again, I can kind of refactor this. We're going to have, let's see, we're going to have the x plus 2 from before. Whoops. We have this x minus 5 now, and then I'm going to use this. That's x squared minus 2x minus 1, except I can't factor that, right? I can't figure out something that multiplies to negative 1 and adds to negative 2. But I do have a way of getting solutions from that. So I know that x plus 2 equals 0 gives me the negative 2 that I have up here. This one is giving me that 5 that I have down here. This, I can get the solutions from something from Algebra 1. I can use the quadratic formula. Okay, think back, way back. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we can use this to help us find the roots here. All right, so if we're going to do that, we have a is 1, b is negative 2, and c is negative 1. So that's x equals negative 2, or negative 2, so positive 2, plus or minus the square root of negative 2 squared minus 4 times 1 times negative 1, all over 2 times 1. All right, so that's x equals 2 plus or minus the square root of, that's 4 plus 4, so 8 over 2. So that is 2 root 2. So we have 2 plus or minus 2 root 2 all over 2. We're going to divide both of those by 2. That gives us 1 plus or minus root 2. So I'm getting 2 different answers from this. So my zeros here are negative 2, 5, 1 plus root 2, and 1 minus root 2. Now, it might be useful to get decimals for those, and you absolutely can. That's going to give me, with the plus sign, about 2.4, and with the minus sign, about negative 0.4, just to kind of be able to plot these on my graph. Let's see, 2.4 is going to be something like this, and negative 0.4, just about negative a half, so something like this. Okay, so we've got our 5 on there, we've got our negative 2, we've got our 1 plus root 2, and our 1 minus root 2. Okay, so now to finish graphing this, we can do just a few things, right? We can find our y-intercept pretty quickly, plug in 0. So our y-intercept is going to be 0 to the 4th minus 5 times 0 to the 3rd minus 5 times 0 squared plus 23 times 0 plus 10, so it's just going to give us 10. Okay, now we can use end behavior. We see the 4th power, that's even, positive, so both ends up. And if I check the multiplicity, nothing had an exponent on it. Everything only showed up once, so we cross through everything. So we're going to go through, whoops, I have to actually hit that that point. So through here, up here, back down, and again. Nothing was bouncing because everything has an exponent of 1.